Okay, so welcome to Math 150 Multivariable Calculus. This is the second lecture on the German tank problem. And my goal for today is to just continue to show you what can you do after Math 150. And one of the most important things to realize is to be useful in the real world, you don't have to get to the optimal answer. You just often have to do better than is being done before. And that's a much lower bar, which is very attainable. So as I said, a lot of this is joint work that I did with some students at Williams. Some other students are going to generalize this further with me. I really want to talk about problems like this because not only is it showing you applications, but it's an opportunity to review a lot of the material we've done throughout the year. So it's a nice way to review the class while seeing something of value. How many of you have ever read a math book or a science book? This should basically be who's awake right now. You know, your hand should be up. You should have read something. It's absolutely amazing. You know, you start off with, say a statement of a theorem, and then you have this wonderful logical derivation that seems like there's absolutely no wasted steps, and everything follows immediately, and you end up with the right solution. The real world doesn't work that way. We don't just start and immediately walk to the final solution. There's a lot of, let me try this path. Nope, this path doesn't work. Let me try that. Nope, this doesn't work either. And so what I want to do today is I want to go down some false paths. So here are some reasonable things to try, and it's going to fail. And then eventually we will find here's a good way of looking at things. The theme today is to try to talk about how data can guide us. So in the first day, this was the theoretical lecture. We talked about how we could come up with the formula, the best fit value of n should roughly be maybe m times 1 plus 1 over k. It was, you had to subtract 1, but that doesn't really make much of a difference. Okay. So earlier in the semester, we talked about the method of least squares. And if you have data that's linearly related, so y equals, say, ax plus b, we had 3 natural choices of ways to count error. Depending on your choice, you can get different answers. So imagine you want to buy a house and you want to find the best house. What is going to make a house best for you? What do you care about? Yes?
The natural lighting.
So natural lighting. So you might care about natural lighting, and that might be extremely valuable to you. Most people would not say that as their first choice, but doesn't mean it's wrong. Number of bedrooms and bathrooms. So you may not care about how big they are. You might just care, I want everybody to have their own bedroom or bathroom. If there is time after class today, I will tell, I don't think it's an inappropriate joke on renting a place that a Williams alum just shared with me. So you might care about bedrooms and bathrooms. What else? Square footage. I don't really want a small bedroom or bathroom. I'm willing to have fewer bedrooms and bathrooms to have things of reasonable size. Anybody ever see the movie War of the Roses? So a couple gets divorced, and neither one of them will give the house to the other. So they divide the house up as to who gets which part of each room. And the husband is explaining this to the lawyer, and the lawyer is going, You're crazy to do this. No. Look, I got more square footage. What else might matter? And this might matter more when you're older and you have children. Location in what sense? Right, so it might be proximity to good schools versus maybe proximity to your work. And so especially for people who work near a big city, things get very expensive as you get near the city. So if you want to have a large house in a good school district, you often have to go far out. And then do you sacrifice the size of the house and a longer commute for a better school district? Well, you might be able to get a larger house as you move further out, but you will have a longer commute. And so how do you weigh these different things? And what you can do is you can assign different weights to the different categories and then try to figure out what is the best house for you for the amount you're willing to spend. How much does that extra, 200 square foot added, how much is that worth to you are you willing to take an extra, 5 minutes on each trip for that? 10 minutes, 20, at some point, the answer is no. Sometimes, of course, you can modify the house. When we bought our house, there was a gigantic room on the second floor, which was just too big. And so we converted part of it to a bedroom, part of it to a laundry room. And instead of having a great room, we now have a good room, which is still big enough for everything we need to do. But you need to weigh all these different things. And depending on your notion of best, you will get different answers. And when someone is trying to sell a house, well, the price they get is going to depend on the buyer. And different buyers will pay more. But I absolutely need this. I absolutely need to be close to campus. I'm willing to pay more. So we have three different choices of what it means to be the best fit. And we've talked about this before. We've talked about how the first one, there's just no way to justify it being good, because positive errors can cancel with negative errors. But the second and third, they both have their advocates. The second treats all errors equally, but the problem is calculus is not available. The third, larger errors count more, but you can use calculus and linear algebra to come up with a closed form solution. And so typically, sadly, the very bottom is converted almost like alien script, but it just says the use of sum of squares as calculus is available. All right. Well, one of the things we saw in Calc 1 and 2 is that if you want to find a candidate for maximum or minimum, you look at either the endpoints or the places where the first derivative is 0. So for multivariable calculus, we look for places where all the partial derivatives are 0. So we take the partials with respect to A and B, and we get a system of equations. We get 2 equations and 2 unknowns. And all that matters is that the relationship is linear with respect to the unknown parameters A and B. It doesn't have to be linear with respect to the x's. It just has to be linear with respect to the unknown parameters. And if we do some algebra and eventually solve, we can get the closed form solutions for A and B. And it's, again, absolutely wonderful when you can get closed form expressions. This is not something that always happens. And a lot of times we have to resort to these Monte Carlo techniques we talked about. Or if you do differential equations, how many of you did the calculus BC exam? Do they have the Euler method problems to solve differential equations where you move forward in steps, very similar to Riemann sums? You do these numerical approximations, and this is a huge field in mathematics nowadays. We talked about how many nonlinear relationships can become linear after applying logarithms. So if I could only have you learn one thing from one of my classes, I would be upset. But if you give me 3 or 4 things, I feel much better. And I easily would use one spot for whenever you see a product, take logarithms. That's one of the things that should become a Pavlovian response. Whenever you see products, think logarithm. And so if we are trying to say y equals bx to the a, this could be maybe Newton's law of gravity, where g is proportional to 1 over the square of the separation. It's linear when I take logarithms to that unknown power. It's y equals a log x plus b. I'm not getting an a squared. I'm not getting an exponential a or cosine a. I'm just getting an a. We now have a linear relationship, and we can apply the method of least squares. So this is an extremely powerful thing. We talked about Kepler's third law. We actually even saw some of Kepler's works, this year. And the big one is the period squared is proportional to the cube of the length of the semi-major axis. This was discovered numerically by Kepler. This was not proven. We didn't even have the law of gravity at this point. His 3 observations were huge starting points for Newton when he was trying to come up with the law of universal gravity. And so he was able to see this by looking at tremendous amounts of data. This is one of the things about the 21st century. This is the era of data science. When I was a postdoc at Ohio State around 2004, I participated in a data analysis seminar. And one of the quotes has stuck with me almost 2 decades later. Every day, the satellites overhead beam down more weather data than there is information in the Library of Congress. And we have a couple of hours to analyze that and make the weather predictions. And this was 2 decades ago. The wealth of data now is absolutely phenomenal in terms of what is available. And so you have to learn, how do I take that data and sift through it and find something meaningful? And a lot of times, looking at data different ways can be very valuable. Doing these log transforms can often make something far more transparent. And so again, if we take square roots, we get period is equal to length to the 1.5, proportional. We talked about what units to use. If we choose units where the distance to the Earth to the sun is essentially one astronomical unit, and the time is 1 year, then we can make that constant equal 1. And this is one of the best straight lines I've ever seen in my life. This is plotting. So I have downgraded Pluto here. The 8 planets. And you see this incredible relationship. This is highly suggestive that the period squared is proportional to the cube of the semi major axis. And so what you can do when you have the ability to look at plots like this is you can make conjectures. Ideally, what would you do after you make a conjecture? So after you make a conjecture, you should, just try to prove it. But if you can't, you can say, well, okay, I can't prove it, but I'm going to use it as a guide. How many of you have ever read the philosopher David Hume? So, just because the sun rose yesterday and the sun rose today does not mean it's going to rise tomorrow. That said, if anybody wants to make a bet with me that the sun will, I'm not allowed to bet with students. I would be very happy to take the sun will rise tomorrow. In the unlikely case that I lose the bet, almost surely there are bigger problems going on than losing that bet. So you can try to use the past as a predictor for the future. It doesn't mean it's going to be right. Do people know about the black swan phenomenon? People are often bad at estimating the probability of unlikely events. I think my favorite example is a newborn turkey. Turkey's born in December, early January. And the turkey's trying to make sense of the world. And eventually the turkey realizes there are these strange beings that walk around and they give me food and drink every day. The purpose of these beings is to see to my needs. And every day the turkey gets more and more data, through February, March, April, September, October, that the purpose of people is to make its life pleasant. What happens in November? So there are dangers of trying to extrapolate too far. I think we talked about adding speeds with special relativity at the start of the year, that speed is not additive. But if you look at small speeds, it's going to look additive. You're not going to be able to see the difference. So the goal of today is not to overwhelm you with large amounts of material. It's to try to just share some stories to just help you think about material in future classes and later in life. Yes?
Is that kind of like, I think in like 2017, Leicester City won the Premier League, and someone put their odds at 2,000. I won 2,000.
Right.
Someone bet it's like $100, and they turned $100 into it's 1,000.
Let me think for a second.
It's like they were so bad historically. So
right.
Like the odds for this.
So the odds might have been reflecting more their previous history rather than the current. So I could absolutely see that. When people are looking at graduate schools and talking to their professors, a lot of times professors remember what a school was like 20, 30 years ago when they were there. And the school could often be very different. Princeton was very different when I went from when people 2 decades before me went. There were absolutely changes. And so you do have to be careful about being too strongly influenced by the past if that data is no longer relevant. Absolutely. We talked, I think, about this bridge, yes? And we talked about Smoot and measuring him. Did we mention what happened to him? Okay, so I will have some slides later. Did we do the birthday problem? I think we did that. And then here is just doing some simulations. And so I did 10,000 simulations where the number of days in the year was chosen from 10,000 to 100,000 and drew the best fit lines. And we proved in the video that it's basically d to the 1/2 square root of log 4. And when we did this over here, if it is d to the 1/2, when we take the log, it should be 1/2 log d plus a constant. And we saw the best fit lines here about 0.506 and 0.481. So both of these simulations are strongly suggesting that the number of days you need grows proportional to the square root of the number of days in the year. You see that there's some fluctuation, but the line does seem to do a pretty good job of going through the middle of the fluctuation. The dots definitely extend further below, but there's more dots above. So this does look like a reasonable best fit line. All right, so here's the German tank problem. This is not supposed to be like a projectile fired from a tank. This is the best fit line. And if you are able to see a linear relationship in this data, you have much better mathematical eyes than I do. So what am I plotting? So the x-axis is m over k. and the y-axis is n minus m. So you say, well, look, I know there has to be at least m tanks. And what I'm going to do is I'm going to choose some number n, and then I'm going to randomly choose k tanks from 1 to n. I'll record the largest serial number, and I know my n should be m plus m over k. I'm sorry, it should be m plus something. I think it's maybe a multiple of m over k. So since I know it has to be m plus a multiple of m over k, or I'm conjecturing that, why don't I just subtract m from n, and I'll plot that. And if you look at this, this looks like an absolutely terrible thing to do. And the reason is, if you think about what's going on, I'm mixing up my variables. I'm mixing up my x's and my y's. And I shouldn't be doing that. And the data is basically telling me, yes, you should not have done that. Right? Let's look at it another way. Let's plot n, or the log of n, against the log of m and 1 over k. So remember, we believe, from our theoretical arguments, that it should be m plus some constant times m over k. If we believe that constant is 1, it would be m times 1 plus 1 over k. So what's the log of a product? The log of a product is the, yes? Not the product of the logs, the sum of the logs, right? Log converts products to sums. Whenever I see a product, I should immediately be thinking logs. So if I believe that it should be m times 1 plus 1 over k, then let me look at the log of n versus the log of the product, the log of m times 1 plus 1 over k. What's the log of a product? It's the sum of the logs. So I get the log of m plus the log of 1 plus 1 over k. Well, remember our Taylor series. If I give you the log of 1 plus x, it's x minus x squared over 2 plus x cubed over 3, and so on. So if k is large, 1 over k is small, 1 over k squared is much smaller, 1 over k cubed is tremendously small, and so on. So I can approximate the log of 1 plus 1 over k with 1 over k. And that's why I'm plotting the log of n against the log of m and 1 over k. And when I use those as my variables, you should see what looks like a plane. And so this is strong evidence in favor of the argument we gave that it should be related like this. All right. So what I want to do now is I want to go through and do some more standard calculations and see some issues. Beforehand, though, I want to talk about trying to get a sense of whether or not an equation is reasonable. So let's talk about, say, playoff series. Imagine you win 80% of your games and you have a 1-game do or die. What is the probability you win in advance? 80%. This is not meant to be hard, right? You win 80% of the time, you play 1 game, the odds that you win are 80%. What if now you have a 3-game series and you win each game independently with an 80% chance? What's the probability that you win 2 out of 3 and advance? Is it 80%? Is it more than 80%? Is it less than 80%? Not 0.8 times 2 is 0.16. First of all, can somebody? Well, 0.8. No, well, whoever wins 2 out of 3 games wins the series. What you could do is, if you win the first 2 games, the 3rd game doesn't matter. You could play them just to continue the humiliation. So I was a postdoc at The Ohio State University. Woody Hayes was a very famous football coach there, and of his many wonderful sayings, one of my favorites was Ohio State was humiliating Michigan. They were up by a huge amount in the 4th quarter, and after scoring a touchdown, they went for the 2-point conversion. And they asked him after the game, why did you go for 2? And his response was, because they wouldn't let me go for 3. So if you want, you could absolutely say, look, just because you've already won the series, we'll still play the other games. It's just the outcome doesn't matter. So you could say, as soon as you win 2 games, it's done. Or if it's mathematically easier, just say, we'll just play all the games and see who wins the majority. So do you think if you win 80% of the time, and now you play a 3-game series, What's your intuition? Do you think you have a greater than 80%, less or equal?
Greater,
Greater, why?
because you're more a large sample size, but 80% to matter, I guess.
Yeah, the odds of you having 2 really bad days is much smaller than just having 1 really bad day. You could also think about it in the limit, instead of 80%, if you had like a 98% chance of winning, then the probability that you would lose, 2 out of 3 games is going to be extremely small. You can write down what the probability is explicitly. What if you start playing more and more games? You win 80% of the time, and now you play 1,000,001 games. What do you think your probability of winning the series is close to? If it's close to 80%, then that means you're losing the series about 20% of the time. You only have to win a majority of games. You win 80% of the time and you play 1,000,001 games. How many games do you expect to win? So first of all, how many games do you expect to win if you win 80% and you play 1,000,000 games? 800,000, and you only need 500,000 to win. So what do you think the odds of winning if you play 1,000,000 games are? Very close to 100%. And as you play more and more games, it should be getting closer and closer to 100%. So before I do any calculations, before I try to see what is the probability, I know that it should be greater than 80% and should be converging to 1 as my series lengthens. So I'm working with some students on a project. I might have told you about who is the GOAT of all GOATs, who's the greatest of all time, of the greatest of all times. This is too hard of a question to answer, it's just a fun one to discuss. And so we've modified it to who's the best of all teammates. But one of the big challenges is how do you compare sports like basketball to football? In basketball, you have long 7-game series. It's much harder, for a weaker team to win, enough games in a 7-game series. But in football, where it's 1 game do or die, much more likely for you to just have that 1 off day or that 1 great day as the underdog and win. And so some calculations I've done have shown that a reasonable exchange rate is about 1.6 NBA titles is worth 1 Super Bowl win. So whenever you're looking at equations, you always want to ask, is this reasonable? You always want to try to put things in context. All right. Yes.
Would you say that from sabermetrics perspective, teachers compare sports like basketball and let's say baseball or hockey, where they come in sort of certain sets compared to a sport like soccer or football, where single matches?
I mean, there's definitely advantages in that. One of the disadvantages of soccer is just you have so few data points in the season. Basketball, hockey, you have on the order of 80 games. Baseball, you have on the order of 162 games. But a lot of it is trying to estimate what is the contribution of the individual. Baseball, you can really split up a lot of what each player contributes. Not entirely, because what I do is a function of who else is on base.
And do you think, I guess, so like statistics-wise, is there like a statistic that's like most important, like WAR or OPS that you use for research?
I like statistics like WAR. I like looking at things, what is the change in the probability of winning after an event. But for a lot of things, you have to figure out, you're not doing this in isolation. You're trying to figure out what is the chance your team will win, how much are you adding. When Curt Schilling signed with the Red Sox for the 2004 season, I believe his contract was illegal because he had $1 million team incentive that if the team wins the World Series, he gets $1 million. And you're not supposed to have something like that. It just wasn't caught. And he said, look, I'm not coming to Boston for individual glory. I've already got a World Series ring. I'm coming here to break the curse and help the team win the World Series. All right. So let's try to guess what the relationship will be in the German tank problem. So we know n is equal to 1 plus 1 over k m minus 1. So let's see if we can see that from the data. So my x-axis is going to be k. It's the max. It's the number of tanks we observe. I'm sorry, no. Sorry, here. K is 1. K is fixed. The x-axis is m, the largest serial number observed. And the y-axis is n, how many tanks there are. So I choose some number n from 1,000 to 10,000. I choose 1 tank randomly from 1 to n, and I record that value of m. So each dot is a different trial. And then I draw my best fit line. So the first thing you should notice is this region looks like a trapezoid. It does not look like a line. The line, sure, I can see that line is maybe approximately in the middle, but this does not look like a good linear relationship. The best fit line, it's saying from the data, is n is equal to 0.784 m plus 2875. Do you think this formula can hold for all values of m? That this will always give you a good prediction for n? What do you think? Are there any issues with this? What kind of test do you have? What do you know about, what relationships do you know between n and m? All right, somebody give me a very nice large round number for m. Huge number. This is just asking for someone to give me a large number. This is not a hard question. A million, okay. So if we take m as a million, this would predict roughly 784,000 tanks. Does that seem reasonable? Why not? Nope. So we observe the largest serial number is a million, and we predict that there are 784,000 tanks.
We should predict that there are at least as many.
Yeah. So what should the slope be in front of m? It should be greater than or equal to 1. So we know just by looking at this that there is no way that this best fit line can work forever. This was a best fit line derived by looking at data from 1,000 to 10,000. The hope is that if you observe a relationship in one regime, you can then apply it in another one. Now you sometimes have to be careful. We talked about velocity or speed is not additive. Yes, but most of us are not traveling at 3/4 the speed of light. Most of us are not traveling fast enough so that this is a real problem. And so for most of us, we can say the experiments we do that show speed looks to be additive in this range is going to extend far enough to be of use. But we know just by looking at this that there is no way that this can work in general. If we look at it a little bit more, we see we've actually done a sin. When we do the method of least squares, the x-axis is what we control, and the y-axis is what we observe. Here, we control n, we control the number of tanks, and then we randomly choose one, and that's the m. We've actually flipped the x and the y-axis. And that's what's leading to the problem here. We're doing things the wrong way. So n is what we're varying, and m is what we're observing. We flipped them. I could try k equals 2. And if I try k equals 2, I get the theoretical line is 1.5 m minus 1. The best fit line is 0.964 m plus 1424. Could this possibly be right? Is there any way this could be right for all values of m? As m gets large, could this be correct? Why not?
Still,
Yeah, same reason as before. The slope is still less than 1. So we go up to 5. Unfortunately, it gets cut off by the zoom window. With 5, the theoretical value is 1.2 m. I know it's a little bit hard to see, but you can definitely see that that's a 1 over there with some stuff that's not 1 following. So it gives 1.037 m. All right, so finally, at least we get a slope that's greater than 1. It at least has a chance. It's wrong, but it at least has a chance of being reasonable. And this is one of the most valuable skills you can get is, can you look at equations and ask, is this reasonable? Can you get some heuristics as to what should happen? If I play more games and I just have to win half of them, then the more games I play, the greater chance I should have of winning at least half the games. All right. So here's another way to do it. We said we flipped the axis. Well, let's flip them and do it properly. Let's put the number of tanks on the x-axis because that's what we're choosing. And then we'll put the observed value of m on the y-axis. It's still a trapezoid, but now when we do the best fit line, your theory is m should be 0.5 n plus 0.5. We get m is 0.496 n plus 10.5. I think that's pretty good for the slope. 0.496 versus 0.500, that's not bad. Now the intercept is different. Okay, but I'm talking about thousands of tanks. Being off by 10 tanks out of thousands is not a huge deal. It's the slope that I care about more. And so we see with k equals 1, if we put the quantities on the right axes, it actually does a really good job. If I do 2 tanks, the slope from theory is 0.667, we observe 0.668. It's just a fluke that it happened to be that good for this run. If I do 5 tanks, the theory is 0.883 for the slope, we observe 0.828. Again, very good. And you can see, just like before, it's tightening up a little bit as we go deeper and deeper, as we have more and more k. There's more of a spread to the above to the left of the line and below to the right. The next thing we could do is we could try to do averaging. Averaging often makes things better. And the problem is just 1 or 2 bad points can really drag you off. So what we do now is for each value of n, I'm going to do 100 runs. So I fix n, maybe n is 2015. I'll do 100 runs, and for each run I record the largest m. And then I average all of those, and that's the dot I put. So every dot here now is the average of 100 numbers. Notice that the variation has gone down tremendously. It's now much tighter about the line. And now, even though I have things on the wrong axis, now theory is that n should be 1.5m minus 1. I'm getting n is 1.496m plus 171.2. So again, by doing a little bit of averaging like this, beautiful fit, absolutely beautiful fit. All right, the last thing I want to do is talk about going one step further and getting a conjecture. So this was all starting with, we believed that n was equal to m times 1 plus 1 over k. And so that's the theory. What if we didn't know that? Could we somehow figure this out? So what we can do is for each value of k, let's try to write n as a function of m. So I'm going to write n as am plus b, but really a and b are functions of k. Which is the more important one, the a or the b? The a, the slope, because as I change m, it's going to, the b is not going to change, but a times m is going to change a lot. So I want to try to plot the slope a against the maximum tank versus k, the number of observations. So the x-axis is the number of observations, it's k. The y-axis is the best slope. Does it look like there's a large change in the slope from the start to the finish? Yes. Is there a large change in the slope from the start to the finish? You're going, what is the slope at the very top? 1.06. And then the slope goes down to maybe about 1.005. Is that a large change? No, but because of the way the graph is done, it looks like it's a large change. One of the things that I do not advocate this at all is do not deliberately mislead with statistics. It is very easy to do so. Depending on how you focus people's attention, you can get them to see certain things. Magicians are wonderful at doing stuff like this. I asked in the first class, who's good at causing people to see things the wrong way, and somebody shouted out politicians. And so I'm not going to make comments on that, but magicians are absolutely wonderful. I think I talked about the amazing James Randi early in the semester. 2 of my friends, left Yale to help him set up his institute. And there was one time when he came and gave a talk at Princeton, and he's at the podium, he's got his glass of water, he's got the microphone, and very easy to hear him. He's got a loud, booming voice, so loud that as he walks away, you can still hear him, but you can't hear him as well as he moves further from the podium. Why do you think it's harder to hear him when he walks further from the podium? Yes. Yeah, because the microphone was off. He had a microphone underneath his shirt collar that he was controlling with a device in his pocket. But it was all these things to get you to focus on the wrong thing. So depending on what you want people to look at, the way you present data can greatly influence what people see. If you want to show a huge impact, I could look at, I think a good example that was talked about was the first time we released gas in the last year or two from the US Strategic Petroleum Reserve. You see gas prices going down by a few cents. And if you just show that range, it's going to look like a huge drop. But if you show the entire price of gas, you'll see, well, it actually didn't go down by that much. Depending on how much you zoom in or zoom out, you can make things look really big or really bad. When I'm looking at this plot, what do you think is going to happen as K gets larger and larger and larger? What does it seem to converge to? Yes, seems to be 1. It could be a little bit larger than 1, but it seems to be at least 1. And we know n has to be at least m, so we know a has to be at least 1. Does anybody know what kind of curve this is? Does this look like any curve you know? Yes. So maybe e to the minus k, that's one possibility. What else? That's one of 2 natural ones, yes. Or 1 over k, that's the other one. And this would actually be 1 plus 1 over k. So those are the 2 natural ones. Now, your eyesight is probably not good enough to determine maybe 1 over k versus 1 over k to the 0.9, 1 over k to the 1.1, 1 over k log k, stuff like that. Similarly for exponential twists. What do you think we could do to maybe try to see what is happening with this data? Nope. We should be having a Pavlovian response. Yes. Take logs, right? Pavlovian response. If you see products, take logs. If you see data, take logs. Do a log-log transform. It should be instinctive. You know, we are in the 21st century. You can have computers do so many tests for you now, you don't have to worry about it. Maybe the data will look better if we do a log-log transform. And so we'll plot the log of A against the log of K. Except I'm not going to plot the log of A, because what do I know about A? It's at least 1, right? So since I know A has to be at least 1, let me plot the log of A minus 1. Okay? And so here is a plot of the log of A minus 1 versus the log of K. Does this look like it is described by a line? I would say so. And the theory is that the log of A minus 1 should be negative 1 log K, because the slope should just be 1 plus 1 over K. And the log of 1 plus 1 over K, when K is large, is just 1 over K to first order. What do we get when we do our best fit line? We get the log of A minus 1 is negative 0.999 minus, I love this, 0.007. Do we all agree that 0.007 is negligible? I'm not trying to put down James Bond. What Star Wars movie has a stormtrooper named THX 007?
Star Wars Christmas special?
No. Yes. Yes. That was the first of the new movies?
Yeah.
Yes, that is the one it was, yes. And THX was because of the movie THX, oh God, it's 1137 or something like that, an old Lucas movie. And that's why his sound studio is THX. But over here, when you look at this, if we just say, replace 007 with 0, we get the log of A minus 1 is negative 0.999 log K. All right, we're all friends here. This is the log of A minus 1 is just negative log K. What's negative log K? That's the log of 1 over K by the power rule. So the log of A minus 1 is the log of 1 over K, which means A minus 1 is 1 over K, which means A is 1 plus 1 over K. And what I love about this is we were able to sniff out the theoretical relationship just by looking at data, by looking at it the right way. What did we do? For each value of K, we tried to find the best fit slope. And we did this for a bunch of values. And then we took that data and we tried to figure out, is there a nice closed form relationship? And there is. And now we have an idea of what we should try to prove. So absolutely amazing what we're able to do with data analysis. So I will, let's see. We did talk about what happened to Smoot. Yes, where he became the chairman. I think I mentioned about the cryptography winter study I taught here. Did I mention that? My first winter study I ever taught at Williams was Introduction to Cryptography, and I encrypted the title. And the college was like, do you really want this gobbledygook to be on your students' transcripts? I said, absolutely. It is going to be a conversational starter. And some of my students told me, years later, you are absolutely correct. I was being interviewed for job. I gotta ask, what is this on your transcript? And it led to good, fun conversations. You were never going to know who's going to be able to help your career. You're never going to know what you're going to have to talk about. This is one of the reasons you come to a school like Williams. You should be able to have a conversation with almost anyone on almost any subject for 15 minutes to an hour. This could range from your football to modern art. After an hour, it's okay to be running out of things to say, but you should at least be able to talk intelligently for 15 minutes on a variety of things. Oh, someone is interested in this. Do I have something I can say? The year I applied for the position here at Williams, I was contacted by a big financial firm in New York wanting to interview me. And they told me that my lunch with somebody from human resources would not count as part of the job interview. It was just a chance to relax and unwind and get some questions answered. And so it turns out she was a former art history major from Williams College. Yep. I am a cultural Philistine, but I can talk about art history for 15 minutes. I talked about Thomas Eakins and the math that was lurking behind what he did with his paintings. And we had a wonderful conversation. And I was one of a very small number of people that she actually remembered interviewing because she had just so many people she saw. And years later, when she had her own company and was helping people find jobs, she put me in touch with somebody who was one of the head analytics people in one of the professional sports leagues. And he came to campus, he talked to my probability class, he mentored several of my students. You don't know what opportunities will happen. Even if something doesn't work out at that moment in time, you may see these people later in your life. Don't burn bridges. Try to think, what can you do to be memorable so that maybe you can work with them again, that they will remember you when they have something else that might fit. All right, so this doesn't have a link to the paper that we wrote. That is available on the webpage, and I've linked that there. I want to just quickly go through, just because I'm recording this, the slides that show how you would do the calculation when you don't know the starting point. So if you now go from N1 to N2, the number of tanks is N2 minus N1 plus 1. The observed minimum tank is little m1. The observed maximum is little m2. The spread is m2 minus m1. And so similar to before, we use the key binomial relationship, and the formula for the expected value of the spread, it's just S times the probability that S equals S. The formula, unfortunately, for the probability is a little bit more involved. And as we start going through, we start having more painful algebra to solve. And you start playing these different games as to how do I write things. And so I'm not going to go through the algebra. If you care, you can go through this line by line. It's not too bad when you have the path. And this is one of the things where experience really helps. The more times you do something, the easier it is. At this point, if you have to do an integral and you see a fraction, you should be thinking partial fractions. You can be cursing, but you go, okay, this is probably going to be a partial fractions. If you see x e to the minus x squared, oh, okay, this is all set up for u substitution. U is going to be x squared, and I've got exactly the x dx, which I'm going to need. The more things you do, the quicker it is, the easier it's going to be for you to see what should you try to do next. When you're starting out, it's very hard, and you just try lots of different things. How can I write things in nice ways? And so it takes a while to go through the algebra. When I do this, I end up having two different terms that I have to evaluate, T1 and T2, two different sums. So I first work on the sum T1, and with a little bit of work, everything comes out and I get a nice formula. I then start working on T2. I play a lot of algebra games, and eventually T2 becomes two additional sums that need to be evaluated with the great names T21 and T22. And you start working with them and you get explicit formulas for them. Turns out everything isn't so bad. And then when you substitute in, you get a nice formula for the expected value of the spread. And then you can just go through and unwind this. And we get very nice at the end, the expected value of the spread is just n plus 1 times k minus 1 over k plus 1. Well, we can then solve for n hats, similar as before, and we get s times 1 plus 2 over k minus 1 minus 1. So again, you're very similar to what we did before. The algebra becomes more involved, which is not surprising, but what's wonderful and not at all clear initially is that there is a good closed form expression at the end of the day. All right, so this is a good place to stop for